Additional funding was provided by Symbolics, Inc., a major manufacturer of symbolic processing systems for developing and running complex software. And by these companies and foundations.
Oh, snake eyes again. Must not be my lucky day. Gambling on dice was a favorite pastime in 17th century Paris. One of those gamblers, a certain Monsieur de Marais, wasn't winning as much as he thought he should. So he asked his friends Blaise Pascal and Pierre de Fermat for help. These mathematical geniuses tackled his problem, and in the process they became fascinated with probability. Their work laid the foundation for probability theory, which has become one of the most powerful statistical tools we have to describe the world. That's because the world is full of uncertainty, and probability is the language of uncertainty. In this program, we'll introduce probability by looking at the long-term relative frequency of an event. We'll learn that probability is the tool we use to understand random phenomena. We'll see that all the possible outcomes of a random phenomenon constitute the sample space. And we'll learn the basic probability rules and how to apply them. In previous programs, we've talked a lot about randomness. We've used tables of random numbers, and we've learned how to design random samples. But what exactly is randomness? At first glance, it seems pretty simple, a completely unpredictable or chaotic phenomenon. But that's actually not quite right. To see why, let's start by looking at something that's definitely not random. Gravity, for instance. If I drop this baseball, it'll fall with the same speed and in the same direction every time. Now what about this? I can't predict whether this is heads or tails. I also won't get the same result every time I flip the coin. So this is clearly not predictable like dropping a baseball. But it's not entirely chaotic either. After all, I know that it's either a head or a tail, and I know that if I flip the coin many times, I can expect roughly half the total to be heads and half tails. So if I flip this coin 100 times, it would come up heads about 50 times. That's pretty remarkable. I can't predict an individual outcome, but I can predict a long-term pattern. This is the signature of randomness. Random doesn't mean haphazard or completely chaotic. It means that there's a regularity that only appears in many repetitions. It's this order that can be described mathematically using probability. Understanding probability is important because life is full of uncertainty, and we have to make choices based on probabilities rather than sure bets. Unfortunately, we're not always expert in gauging those probabilities.
What do you most fear could hurt or even kill you? Nuclear power? A leaking toxic landfill? A handgun? A plane crash? How about a car accident? Well, people who study risk say that we should worry most about car accidents and consider ways to prevent them. But we don't. Why? Well, maybe because we over-exaggerate the threat of sensational yet rare ways to die and underestimate the probability that we could hurt ourselves during an everyday activity like driving.
Do you think you're an average, above average, or below average driver?
I'm a little bit above average driver.
I'm at least average to above average.
Definitely above average.
I'm above average.
How about you?
Don't believe me, he's below average. Look at him.
80% of people in most countries believe that they are safer than the average driver. Now, that obviously couldn't be the case. More than half of people can't be better than average.
Dr. Baruch Fishoff is an expert at evaluating the probabilities of injury or death in everyday life. Probabilities that seem so negligible, we choose to dismiss them.
A rough estimate is that about 1 trip in 4 million in the United States ends in a fatal accident, and about 1 trip in 100,000 ends in an injury accident. So those are really very small probabilities.
Because the odds seem so small, we don't think twice before climbing into the car. We ignore the small but measurable odds that our daily activities will hurt us. Why? Because we examine everyday risks too subjectively.
People rely on their experience, that they're often pretty good at remembering their own experiences, but it often doesn't occur to people to ask whether their experience has been misleading, and that it's difficult to make a systematic analysis of how your experience might have misled you.
Because we rely on our own experience, we don't believe the odds apply to us.
What do you think your chances are of dying in an automobile accident?
Well, supposedly, statistically, 1 in 500 or so, or 1 in 1,000 or something, but I don't think my chances are, are very likely.
I'm very careful. If it will happen, it will be the other guy's fault.
And even when we know the odds, like the chance of a fatal accident, 1 out of 4 million car trips, we have difficulty making sense of the information.
It's difficult for people to see how quickly these risks accumulate over repeated exposure. Try to think about how many car trips you take in your life. It's almost hard to believe, that something that on every car trip there's almost no risk, and yet over a course of a lifetime it might be 1 in 100 chance of being in a fatal accident. There's something unintuitive there.
I want you to think about the chances, the probability that you might ever in your life get addicted to alcohol.
Probably about 10%.
Risk and decision-making research is now focusing on teenagers. After all, it is during our teen years that we adopt habits that may last a lifetime.
Nathan.
In interviews and surveys, researchers were surprised by the way teens assessed risk.
I think if you talk to teens, you often find that they have a much more complicated way of looking at the problem. They know that there's a lot of social pressure on them to smoke in particular social settings, and they just don't want to buck that. To put it in extreme terms, what do you care if you're going to lose, you have some chance of losing 5 years of your life at the end if you don't think you're going to make it out of high school alive?
So risk experts try to convince teens to take fewer chances by tailoring the message to fit.
Tell me, baby, why you smoke that trash?
It's a different challenge to convince adults with their ingrained habits to modify risky behavior. How can it be done? By looking at the long term, a lifetime of experience when evaluating everyday risks. Wear a seatbelt and you will cut by 50% your chances of dying in an auto accident. Don't smoke. Don't drink to excess. Eat a balanced diet. Wear a bicycle helmet. Not startling advice, but it's what long-term probability dictates as the most predictable way to survive.
I think what statistics does is summarizes experience in a way that will help people to make decisions. And those can be scientific decisions or decisions in their own lives.
Probability gives us a systematic mathematical way to make decisions and predictions. Our exploration begins with this coin. If I tossed it 10 times, I might get 3 heads and 7 tails, or I might get 6 heads and 4 tails. The proportion of heads, which we call the relative frequency of heads, could vary a lot. Let's keep track of heads over the course of many tosses. The first toss was a head, so the relative frequency is 1. The next toss gives a tail. Since I've had 1 head out of 2 tosses, the relative frequency is 0.5. Then I get another head, and the relative frequency becomes 0.67. As more and more tosses are made, the heads and tails begin to balance out, and the relative frequency of heads gets closer and closer to 0.5. This fact has been demonstrated many times. During World War II, while he was a prisoner of war, the English mathematician John Carrick flipped a coin 10,000 times. He recorded 5,067 heads for a relative frequency of about 1/2. Based on this relative frequency, we can say the probability of a head on any single toss is 1/2. Before we move on to learn some basic probability rules, Let's drop in on someone who can show us something of the richness and subtlety of the field of probability.
Mu is greater than C plus the sum of...
As he quickly works through a proof of probability law, Percy Diaconis is center stage.
Is that okay with everybody? What I did here to get this inequality is I said, forget about the p's. This event...
But it was a different kind of stage that first fired his imagination. As a boy, he was more interested in magic than in school. At 14, he ran away from home and hit the magic circuit under the stage name Percy Warren. After 10 years on the road, Diaconis returned to school to learn more about probability and randomness, subjects he'd become fascinated with as a magician. He is still in school, now as a professor of mathematics at Harvard, and one of the most original thinkers in the field of probability.
I've spent years analyzing the basic images of randomness that we have. Coin tossing, shuffling cards, flipping tacks, rolling roulette balls. And two things have emerged. First of all, it's possible to make things random. If you flip a coin quite vigorously, it's as close to being a fair event 50-50 as I know if you flip it and catch it on your hand. If you shuffle a deck of cards many times, 10 times, they'll get all mixed up. So one thing is, the usual ways we try to randomize usually work pretty well if you do them vigorously. However, we usually don't do them vigorously.
In short, Diaconis tells us we need to revise our notions of randomness.
To start someplace, consider flipping a coin. That, for many people, is just a very, very fundamental image of a random phenomena. And yet, if you think about it the least little bit, you'll realize it's not random at all. In fact, there are people around carnivals, and I, on occasion, have been able to flip a coin and keep control over it. Let's see if I can still do that. I don't know, here's a coin. It's an ordinary $50. It's got a head on one side and a tail on the other. And if I do flip it like that, it should be that it's heads. It's actually rather complex what I'm doing. There's heads.
With skill honed by long practice, Diaconis can make a coin come up heads on every flip.
It is surprising when you first see it. I know that I can toss it and make it come out however I want, but you don't know that, and for you, you think all sequences are equally likely. It's kind of clear that what probabilities are assigned to a coin toss has something to do with what you know about the person tossing it and the coin being tossed and things like that. And that kind of thought has led a group of us to say that probability isn't a fact about the world. Probability is a fact about an observer's knowledge. Let me write this as
This idea is typical of the kind of creative insight Diaconis has brought to the field of probability, a field that continues to challenge and delight him.
I love when somebody comes to me with real data that has all of its full uncertainty in it, because I know that I will be able to, by taking appropriate averages, find the structure that's hidden in that data. So for me, having some ability gives me real joy in facing uncertainty.
Percy Diaconis is expanding and challenging our notions of probability and randomness. That kind of thinking is important when it comes to advancing science. But it's also important to have a good grasp of the traditional definitions and rules of randomness and probability. Random phenomena exhibit a pattern over time. We can measure that pattern as long-term relative frequency and then actually assign probabilities. For example, I know that only 2 outcomes of a coin toss are possible, either heads or tails. The collection of all possible outcomes for a given phenomenon is called the sample space, or S. In this case, our sample space for a single coin toss is 1 head or 1 tail. We can write that like this. Suppose we toss the coin twice. Then the possible outcomes would be 2 heads, a head then a tail then a head, or 2 tails. That's the sample space for 2 coin tosses. A combination of outcomes is called an event. For instance, we could ask about the probability of the event a head and a tail in 2 tosses of the coin. 2 different outcomes could produce this event, a head then a tail, or a tail then a head. Another event is at least 1 tail. In that case, the event consists of 3 possible outcomes, these outcomes here. We can use this language to construct a probability model. This consists of 2 things, a list of all possible outcomes and an assignment of probability to those outcomes. Let's make a probability model for the roll of a die. The possible outcomes are the numbers 1 through 6 on the die. So the sample space contains these 6 outcomes. The die is balanced, so we can realistically expect each number to appear about 1/6 of the time over the long run. We can therefore assign a probability, abbreviated P, of 1/6 to each of the 6 outcomes. Now, the probability of any event is just the sum of the probabilities of the outcomes that make it up. For example, the probability that we roll an odd number is 1/6 plus 1/6 plus 1/6, or 1/2. The probability of rolling either a 6 or a 1 is 1/6 plus 1/6, or 1/3. This example illustrates 2 general rules of probability. First of all, the probability of any event A in a sample space is always between 0 and 1. Second, the sum of all the probabilities in the sample space S equals 1. A probability of 1 means absolute certainty. So all we've just said is that if we roll a die, it's certain that one of the 6 faces will come up. Probability models are used all the time, and for understanding a lot more than dice and coin flips. For instance, they're often used in studies of seemingly unpredictable behavior, like the way everyone else seems to drive.
The city of New York has some of the worst traffic in the world. Take it from the people who drive there for a living.
The rush hour is terrible. It's like a parking lot, all the city, any place you go.
Trying to make the situation a bit more manageable has been a difficult challenge for the city, perhaps because traffic is, ironically, a sign of the city's success.
As long as we're going to have a prosperous New York, traffic will be there. And so therefore, traffic per se is not better. What we're doing is, by using different engineering tools, we are able to manage traffic better.
Link 1013.
One of these tools is NetSim, a probability-based traffic simulation model. With NetSim, traffic engineers can assess the effect of possible improvements, like adding a left turn arrow or widening a roadway, without having to actually make the changes. Mark Yedlin was one of the major developers of NetSim.
Rather than going out in the field and actually causing disruption to traffic by implementing some strategy which may not work, they have the ability through this type of a tool to be able to study the effects of traffic flow changes and view them on the screen as we see here.
These symbols represent stoplights, either red or green. These short yellow rectangles are cars, the longer ones are buses. To determine the speed and behavior of each vehicle in the model, the random behavior of real motorists is observed over a long period of time. Eventually, patterns and consistencies emerge. Based on these observations, probabilities are assigned to each vehicle.
Every decision that is made within the model in representing driver decisions is a probabilistic one. For example, there's a probability that a driver will decide to make a specific turn. Probability for each turn movement, in fact, so that one specifies what the general probability is. In other words, there might be 10% right turn traffic and 80% through traffic and 10% left turn traffic on each street. And the model will take those individual probabilities and will apply them. We have various driver aggressiveness characteristics represented in the model as well. For example, some of our drivers will become quite impatient upon an amber signal and will accelerate and go through. Others will decelerate and stop. At the onset of a green signal, some drivers will very quickly accelerate and pull out of the intersection, whereas other drivers will be more restrained. We represent 10 different levels of non-aggressiveness to aggressiveness characteristics. Each driver has a specific desired speed in mind that he will try to achieve along each section of roadway.
One traffic problem under study is this stretch, 5th Avenue from 54th through 65th Street. It has some of the worst traffic in New York. Especially bad is the intersection of 58th and 5th.
People who is crossing the city, they gridlock always in the 58th Street. So they hold the traffic that is going through the 5th Avenue.
Here we see the beginning of spillback, a precursor to the dreaded gridlock. The traffic on 5th Avenue has a green light, but the cars on the cross street haven't yet cleared the intersection. Spillback occurs when drivers enter the intersection even if they can't move through it. There is a measurable probability that a driver will make this decision. And it is the use of these probabilities that allow the computer to model this scenario with astounding accuracy.
We have several vehicles which have entered the intersection of 58th and 5th Avenue, intending to travel along 58th Street. However, they have no place to go, so they block the intersection. And we see that although traffic on 5th Avenue sees a green signal, these vehicles are blocked, and these drivers are experiencing considerable frustration.
The first step is completed. The computer has accurately represented a real traffic situation. Now comes the most important part. Using the known probabilities for driver behavior, traffic engineers can experiment with changes until a clear improvement is found.
At this point, we're seeing a new signal timing plan implemented, in which we provide the same amount of green time to 5th Avenue, but we provide it when the vehicles can utilize it. We've also changed the timing on 58th Street as well to eliminate the queuing situation and the intersection blockage that took place at 58th and 5th. We were able to see approximately a 27% increase in speed along 5th Avenue and a 48% decrease in delay, which are rather substantial statistics.
So Mark Yedlin knows exactly how these changes will affect 5th Avenue, even though they haven't been implemented yet. This striking ability to mirror a process like traffic depends on the use of probability.
Traffic flow is a very random process. No two drivers behave exactly the same way. Neither do vehicles perform in identical fashions. So given the random nature of traffic flow, probability plays a major role in being able to describe these processes.
Now let's say we're traffic engineers and we want to plan for the different kinds of drivers who are likely to pass through an intersection one at a time. Our possible outcomes are 6 types of drivers. We'll label the types hot rod, running late, commuter, dad, student driver, and Sunday driver. The 6 types move at different speeds and have different probabilities for entering the intersection. In this case, my sample space, abbreviated S, is the set of 6 drivers. I've assigned probabilities to the driver types based on their prevalence. Hot rod, for instance, is fairly unusual. He only comes through the intersection 1/10 of the time, so his probability is 0.1. Running late and commuter are more common. They each have a probability of 0.2. Dad is the most typical, with a probability of 0.3. Both student drivers and Sunday drivers are relatively rare. They each have a probability of 0.1. Since each probability is between 0 and 1, and since they all add to 1, the model obeys the probability rules. Let's look at the probability of some possible events. Remember, only one driver can be in the intersection at a time. What about the probability that the next driver in the intersection will be either a fast or a slow driver? We could call the first event, event A, a slow driver. It would consist of a Sunday or a student driver. Event B, a fast driver, would consist of either hot rod or running late. These events, A and B, are disjoint, meaning they have no outcomes in common. Because they're disjoint, the the probability of either one or the other occurring is simply the sum of their respective probabilities. In symbols, the relation between disjoint events is written like this. The probability of A or B occurring equals the probability of A plus the probability of B. In our example, A is the probability of finding a slow driver in the intersection, and B is the probability of finding a fast driver. The probability of finding either a fast or a slow driver in the intersection is simply the sum of the probabilities for the two groups, which is 0.2 plus 0.3, which equals 0.5 or 50%. 50% of the time, we will find an atypical driver in the intersection. That's important information when we need to figure out the traffic flow through the intersection. So when you want to find the probability of one event or the other occurring, you add the probabilities. This simple yet very handy and fundamental rule is called the addition rule of probability. We've now learned three basic rules. The probability of any event is between 0 and 1. The probability of the entire sample space equals 1. And the probability of either of two disjoint events occurring is the sum of their individual probabilities. In our next program, we'll expand our probabilistic tool chest to include ways of dealing with a broader range of problems. Maybe my luck will improve by then.